All right, so what we've been doing, everybody, is testing hypotheses, and because you're already confused, we're going to try to make you more confused today by throwing in some different kinds of hypotheses. Kind of, just kidding. Actually, what we're going to do is sort of start to think about your statistics book as a cookbook. That there are different kinds of hypotheses we have about different kinds of data, about different kinds of summary statistics, and there's different mechanisms and methods for testing these different hypotheses. We've already tested a couple, and we're going to add a couple more to our repertoire of recipes, but understand that statistics book you have is full of a bunch of other ways to test hypotheses. So if you find yourself facing a different set of circumstances, you might simply need a different kind of hypothesis test. So what are some of the different kinds of relationships that we're going to test in this course? How likely is it that my observation came from the same process, came from a better process, came from a worse process? How likely is it my mean came from the same population as that other mean? Those are the two kinds of tests that we've already done. How likely is it that two sample means came from the same population? Are two means different from each other? This is a fairly common kind of question that we want to answer. It's actually probably closer to what we wanted to answer than that funny, how likely is it my mean came from the same population as that other mean, right? A fairly common question is I have two sample means. Are they the same as each other? Did they likely come from the same underlying population, or are they actually different? Then sometimes we have questions about proportions. How confident am I that a sample proportion represents the population proportion? Are two proportions the same? Are more than two proportions the same? Is there a relationship between two variables in a linear regression? We're going to get there later. Another kind of hypothesis that we're going to test. So far we've asked how likely is a given observation if the underlying distribution of something is normal? How likely is it that the next repair time is 52 minutes? How likely is it that an individual will score 37 on the exam? For these, we use a normal distribution with sample of population mean and standard deviation. We can also do this for individual observations with other underlying distributions. Something like, how likely is it that 3 out of the 4 businesses you call will be owned by women? This would be a binomial distribution. Right? We can use those other distributions that you've studied to answer other kinds of questions and do other kinds of hypothesis testing. So let's say we want to ask, what is the probability that a randomly selected student scores 37 or below, or 37 or above? We could also ask, what is the percentile for a score of 37? Or we could ask, what is the range for 90% of student scores, right? Get a confidence interval. We like to map, right, our information to the standard normal. So 40 is the mean here, 46, so a standard deviation of 6, right, and a score of 37, the x value here. Is it about negative 0.5z? If we want to go ahead and do that using R, we would use the p-normal function and find out that everything to the left of that 37 is about 30.9%, right? Approximately 31%, and everything to the right about 69.1%. Asking what is the percentile is simply another way of asking the same question as in number 1, and we would get about the 31st percentile. If we wanted to build that 90% confidence interval, we would use the Q-normal function, and we get somewhere between 30 and about 50 would give us our range of scores. Then we went and asked questions about comparing sample means. So here we're asking, is something different on average? According to the central limit theorem, means from any process are normally distributed. This is why normal distributions are so handy. And we can use the standard normal distribution if we have sufficient n, which means n should be greater than 30, right? So we need at least 30 observations. Means are more tightly distributed than observations, so we have that special standard deviation, the standard error, which is the standard deviation divided by the square root of the number of observations we have. And this means that standard errors get smaller with bigger sample sizes because we are getting closer and closer to the population. So the bigger my sample, the more likely, the more it looks like a population. And if the underlying distribution is tighter. So some examples of some average kind of questions. If repairs in my shop have taken on average 70 minutes, how likely is it I will observe an average of 80 minutes or 30 minutes from the same process? If historically the monthly average has been that we pay our bills in 31 days, what is the range for 90% or 95% of monthly averages? If historically the monthly average has been that we pay our bills in 31 days, what is the likelihood we could have a monthly average of 40 days if there's no change in the process? If subsequent classes come from the same population of the students, what is the probability of a class average of 41? So let's take a look at that exam score. Let's say class averages in the past have had an average of 40, a standard deviation of 6, and we have an N of 144. If subsequent classes, come from the same population, let's come up with a 99% confidence interval. All right. So our standard error here is about 0.5. Right? And that standard deviation of 6 divided by the sample size of 144. And we could do all of this by hand, but we can get our our probability, right, our p-score from our normal distribution of 41. There's about a 2% chance that you would see that, right, 2.25% chance that you would see that even if things are the same. If we want to build a 99% confidence interval, we split up that 1% and we put 0.5% in the one tail and 0.5% in the other tail and use our Q normal function. And that's going to give us that our 99% confidence interval is somewhere between 38.71 and 41.28. Now, we've done those kinds of tests before, but one reminder, are we asking to be 95% confident that the new class is different? Then its mean should lie outside both tails. Right? Are we asking to be 95% confident that the new class is better? Then its mean should be greater than or equal to the 95th percentile. We can also test whether there are different means between two groups or two samples. Both samples need to be at least 30 to assume that this is normal. So before we were asking, did the new class come from the same population? We might want to ask, is the new class average different from an old class average? Or do these two samples come from different populations? We might want to ask, how likely is an average repair time of 26 minutes in our old process? Or we could ask, how likely is it that the new average repair time of 26 minutes is different from the old repair time of 60 minutes? The math for two means is a little bit funny. It's a little bit messier, which is why we usually postpone teaching it, even though I think it's a little bit more practical and a little bit more handy. So what you're going to do is you're going to take the standard deviation squared for both the new and the old, right, the two means, and divide them by their ends, and you're going to add the two together, and you're going to take the square root of the whole thing. And that's going to give you this kind of, if you will, average standard error across the two means, right? It's kind of funny averaging technique, squaring and square rooting. And you're going to set your H naught, right, your 0 on the normal distribution to be the difference between the two means. So the hypothesized difference between the two means. So often this means our hypothesis, our H naught, is that the two are the same. So we would set that at 0. So often 0 goes at 0. And then we use the standard errors to build out our distribution. Let's go ahead and do an example, and we're going to take a look at this example and do some calculations in R. So we get this fancy standard error, this average standard error of the two. We can go ahead and come over here to R and calculate this standard error. It's going to give us about 2 1/4. We're setting our null hypothesis at the idea that the two, right, at the idea that they're 0, and our test statistic is going to be the difference between these two means, 44 minus 40, which is going to be 4. But let's go ahead and set up our normal distribution here. We have a 0, right, as our null hypothesis, our kind of x's. Each standard error, so this is going to be at 2 1/4. This is going to be at 5.5 and 7, right, 0.75. And over here you would be at, right, minus 2 1/4, etc. Now we take our test statistic. Let's change colors here. Our test statistic, x is at 4. So kind of right about in there. And we're going to try to figure out, we're going to let R help us figure out what's going on here, right? How likely is it we would observe a 4 if the new isn't really better than the old? So we're going to go ahead and let R calculate the standard error, set the null hypothesis and the test, and I find that that's handy because then I can go put it back into the normal distribution in a slightly funny way and go ahead and come up with that probability. Because we're looking for that right tail, that's why we give it that lower tail equals false. And we get that there's about a 3.8% chance, right? So our p-value is 3.8%. All right, folks, one caveat here before we move on after that example is that often you'll find in statistics textbooks they talk about t-distributions and using t-tests rather than z-tests. These are fairly similar to z-tests, but we use them when n is less than 30. So when n is less than 30 for either sample, we would use a t-distribution rather than the standard normal. And the t-distribution simply has heavier tails than a standard normal distribution, especially for smaller samples. So the smaller the sample with a t-distribution, right, which means the smaller the number of degrees of freedom, which is stats for n minus 1. So if it says degrees of freedom equals 3, that means n is equal to 4. So the smaller the n, the fatter the tails of the t-distribution. The reason I'm going to teach this to you in terms of z instead of t is that almost always we end up with large enough samples. Frequently we end up with large enough samples. We're going to keep things easy here. And once you get to n equals 30, t and z are virtually indistinguishable from each other. If you wanted to use a t-statistic instead, you would need to calculate the t-statistic instead of that z-statistic that we've been calculating. And you do it in much the same way. You take you can set the null hypothesis, and you go ahead and test for how far away that t-statistic is from your null hypothesis. So the test works much the same way. It's just simply what we do when we have small samples. And we need to know what that sample size is to be able to use, right, that t-test with a certain number of degrees of freedom so that it knows which t-distribution to use. All right, let's go ahead and go back to R and talk a little bit about testing a sample with proportions. So what's cool with proportions is they work pretty much the same way. Proportions are normally distributed according to the central limit theorem as well, as long as the proportion times the number, so you take your total n of your sample, as long as the proportion on both sides, right? So if you have, 70-30, 70% times n and 30% times n, both need to be greater than 10, right? So we need that's kind of our sufficient n condition. It's called the power condition to get the central limit theorem to work in the case of proportions. But once we do, proportions are normally distributed too, and we can calculate a standard error using this formula of the proportion times 1 minus proportion, the calculated proportions, divided by n is going to give us the standard error. And we're going to use and build confidence intervals and do similar things using proportions. So here's an example for you using the proportion of Americans that support nuclear arms reduction. We have a sample of 1,028 U.S. adults in March 2013 that says that 56% support nuclear arms reduction. You take that proportion, we'll call it p hat, it's the estimated proportion. We have the sample size of 1,028. Does the central limit theorem work? Yes, because we have 575.6 on one side, 452.32 on the other. That means both sides are greater than 10. We can calculate the standard error. And then we can go ahead and calculate, right, a confidence interval for our population parameter, or the true population proportion here, this 95% confidence interval using Q norm, just like we did before. We're just simply using this different standard error and a sort of different, our proportion instead of our mean. We can also test the kinds of hypotheses we've been testing about our proportions. So building these different confidence intervals, a 95% confidence interval, and we can set a null hypothesis for something like that the proportion is roughly 50%, and an alternative hypothesis that it's not 50%. The central limit theorem is going to work because we have if, right, there would be enough people on both sides of this proposed hypothesis, 514 and 514. We calculate the standard error based on the proposed hypothesis and build our confidence interval around our sort of proposed hypothesis from our sample size, which is a little weird. Admittedly, we're using this 50-50. Proportions are weird in other ways. We often report margins of errors from multiple things. We typically choose, right, the highest standard error when we do that. We often assume that the proportions are 50-50 because this is the most restrictive. It's going to build the biggest standard error and going to give us the biggest sort of margin of error. When we're comparing two proportions, we use a normal distribution. When we want to and use what we would call a combined or pooled standard error. When we use multiple proportions, we go to a chi-squared distribution. So this is another case where it's like statistics is like a textbook. In fact, that's kind of where I want to end today, right? We've just scratched the surface of hypotheses you can test. Given you a couple of examples, we're going to work through some of them. Choosing the right test is half the battle. I must admit, I go back to my statistics textbook every time I need to do another kind of test. Sophisticated software makes the tedium of these calculations easier, but you need to think through what the appropriate test is and whether you can use the normal distribution or need something else, and how we go about testing our standard errors and test statistics and then employing that distribution. So there's a little bit of thinking, a little bit of referring to the cookbook, and thinking through the appropriate ways to get things done. With that, I'll let you go ahead and continue practicing some of these kinds of hypotheses tests, and we'll work through more examples until we get to where we feel comfortable, at least with a couple of different kinds of tests. Thanks.